It's just
I
saying on the
understand.
left. Now it's streaming, so.
Yep, we're good.
Okay, I see the button.
Okay, so just want to welcome you all again to the Samir's class, and this time Bingro and Mathur have volunteered to take us through it, but I'll ask Samir to start by just giving introductory comments, and then we'll take it from there. Over to you, Samir.
Okay. Yeah, thanks to everybody for coming for the session. So I hope you have all looked at the problem set 3. And what I'll do is I'll just try to give an outline of what where we were with the entire story and what the goal of these problems is. And then as we go through, we'll go through a couple of problems by Bin and Mathur, and then we'll stop after every couple of problems and maybe talk about the physics. People can ask questions, then we can again go. Maybe after each question, we can stop and see if there are questions and talk about the physics. So let me try to screen share my iPad. Okay, so you should be able to see the iPad up there. And so just to remind ourselves, what is the problem that we are addressing? So in the first assignment, we learned that the black hole inside has an infinite amount of space. So the black hole interior has infinite space. And that's because outside, for r bigger than 2m, a space-like slice is like t equal to constant. But for r less than 2m, because the metric changes sign, a space-like slice is r equal to constant. And so if you try to draw the whole thing in, let's say, Eddington-Finkelstein coordinates, so you can put u here, but most importantly, we have r on this side, and here is r equals to m, and here is r equals 0. Then you find that the horizon is here, and then if you draw one slice like this, then if you try to draw a later slice, keeping t equal to constant here, but still not trying to go too close to the singularity, so you advance it very little over here, then the slices, as you can see, will stretch. And the main point was there is no way to slice the black hole geometry so that each slice is isomorphic to the previous one. If you could do that, then whatever that slicing is, that particular slice geometry, you could take the lowest energy state on that geometry and it will stay there. Then you would have no pair creation. But if all the slices have to keep stretching, it's a bit like the cosmology, that the cosmology is expanding, so the metric is changing, and so whatever you thought was the vacuum at one time, it will not be the vacuum at a later time, and that's where the particle creation comes from. So if you take this and then you, let's say, start with any given surface, and suppose you start with the vacuum on the surface, and then for the time evolution, let's just evolve it perpendicular to it at every point, then you find that what is happening is that the slice is stretching. You can see it becomes longer. And when you stretch a slice, then you actually get particle creation. So this geometry is what we learned from in the first assignment. But in the second assignment, we saw that if you take quantum field theory, it is nothing more than balls and springs. Some mass is m joined by springs. And then the oscillations of these balls, because of these springs, basically gives you the scalar field. This is directly modeling the scalar field. And so now you can see if somebody gave you a slice and you had points on it, let's say this was the horizon. And so this point was called 1, 2, let's say 3, 4, and so on. And then suppose they stretch, that the distance between 2 and 3 becomes bigger. So they stretch. And then you will actually get particle creation, because now you can say that the spring joining these, which was like contributing to the harmonic oscillator, now has a different spring coupling. So this was asked at the end of the last session, why does it mean that the spring coupling is going down? And we said that the Hamiltonian is equal to grad phi mod square, which you can write as phi at 0.3 minus phi at 0.2 upon x3 minus x2. These are the coordinates I've given. You take the square, but then you multiply by g upper xx, right? Because this is del phi by del x squared, but you multiply by g upper xx. So when the 0.2 goes here and the 0.3 comes here, if the separation between them has increased, then gxx has gone up, increases. And that's the same as saying that g lower xx decrease, g upper xx decreases. So you see the harmonic oscillator, the Hamiltonian in the harmonic oscillator, which had this quadratic term, which was coupling the oscillator at 0.2 and 0.3, the coefficient of that is going down. So we see that the way to make a toy model, which actually has all the essence of what you need, is that you have two harmonic oscillators and they are initially coupled by some cross term. So you have coupled oscillators. And if you take two coupled oscillators and you put them in their ground state, and then at some point you break the coupling, so you just have two oscillators, then you find that this was in the ground state, the O. Then when you write the state in terms of the two separate oscillators, you find it's not actually the vacuum. It is some bit of the vacuum, but then you will have A dagger 1 on the first times A dagger 2 on the second. So one pair of particles and then two pairs of particles and so on. So you see that the state is entangled. The state of this is either this times this or this times this. So you have a sum of states. So you can see the whole thing is entangled. And so that brings us to what we are planning to do today. We now want to learn how to measure entanglement. And all the information that you need in here, I'm sorry, I forgot to write it on the slide last time, but I hope you have been looking at the Gyan lectures whenever you need them. So in the Gyan lectures number 9, you will see all the basic introduction of what is the density matrix and so on, which you need to define how to measure entanglement. So what we're going to do in this particular assignment is just learn how to measure entanglement. And the basic idea of entanglement is that if we have some system made of, let's say, two parts, let's call them capital A and capital B. So you have parts A and B, then the total state of it can always be written as a linear combination summation over I. And then you can have Cij, some state psi I of the first one times some state chi j of the second system. So this is of course completely general because these form a basis for the entire system. What is nice is that by making a unitary transformation on A, system A, and a unitary transformation on system B, two completely different unitary transformations, you can always write this in the form summation over I, some coefficients, let me call them bi, times some psi I primes, times chi j primes. So you can basically always sort of diagonalize that. And roughly speaking, if you want to see what an entangled state is, it counts how many pieces there are in the sum. So if you had a state psi, which was of the form 1 over root n, and then you had psi 1 times chi 1 plus some state psi 2 times chi 2 and so on. If you had like n states and psi 1 to psi n were orthogonal, chi 1 to chi n were orthogonal, this is the simplest state which you can write. This is what is called a maximally entangled state. There are n terms in this. And the entanglement entropy of that, which we call S sub ent, is equal to n times log 2. So it's log n. If there are n pieces like this, the entanglement entropy is log n. Okay, so we know the entanglement entropy just says how many pieces there are in this kind of sum. If it is just something here times something here, just a factored state, you can see its entanglement entropy is 0. If there are two terms, something times something plus something else times something else, the entanglement is log 2. If there are three pieces, it's log 3 and so on. So that may look very simple. The only problem, of course, is that this kind of state, which is actually what's called a maximally entangled state, is not what you always get. In general, you will have all kinds of coefficients. You can diagonalize them up to like this form. And then the density matrix of that you can compute from the DI. And that's what you learn in the problems here. But you can see from this that everything you need to know about the Hawking problem is here, because each pair that is produced, each time a harmonic oscillator gets excited in a pair, you get an entanglement of log 2. And what one of these problems will show you is that after you emit n pairs, the entanglement of the outside with the inside becomes n times log 2. So they're n different pairs. And so that is the page curve for a basic, the lowest order Hawking calculation as you go through the number of steps, which is equal to the sort of like keeping track of the time, the entanglement which you plot on this side just keeps linearly increasing. Okay, so that's the page curve that you have heard about. And then when you get to the end point of evaporation, the problem is your radiation is entangled with whatever is left behind, but there's no mass left behind. If there's no mass, there can't be any states if the black hole is evaporated. If there are no states chi, then how do you actually make the entanglement? So that's the quantum mechanical problem. If you are entangled with something, but that something doesn't have any states, then it doesn't make any sense. So then you have to break quantum mechanics or say that thing is a tiny remnant with a lot of states, but whatever you do, you get into a problem. So this is the reason we have reached whatever we have in this assignment. And so what we are going to see is how to measure entanglement. But again, just to summarize, the entanglement we are measuring is because we end up creating particles, and we create particles because space-time stretches. So in the first assignment, we learned why space-time stretches once you have a horizon. And so it keeps on stretching as long as you have a horizon. That's why black hole keeps on producing particles. Then stretching basically creates excitations that you can see from a toy model of the scalar field and harmonic oscillators. Everything you want is in this toy model. So You don't have to think it's too toy. It's sort of okay. And then just to measure entanglement, whatever you're seeing here from the toy models will tell you that this is the page curve and that is the entire paradox. Okay, so that's all I wanted to say. Let me see if there are any questions for me at this stage. And otherwise, I'll just turn it over to Bin and Mathur to see what they want to say.
Before we turn over to Bin, I just want to say it'd be great to have a volunteer for next week to do the sort of guidance through the problems. Next week's problem set is about what again?
Okay, so next week I was planning to tell people about black hole entropy, in particular the Euclidean calculation of Gibbons-Hawking entropy, because that is what tells us what all the island people are going in circles about. So we will basically see what they always keep using Euclidean, and their whole confusion is that the Euclidean Gibbons-Hawking answer was always the finite answer. If you see that if you claim that that is the entropy of the black hole, there was nothing to solve right from 1976. So they keep using the Euclidean answer and confusing that with the problem of saying that you're solving the information puzzle, and they still keep a smooth horizon. So now from the next assignment onward, we'll try to bridge the gap between what the island people are doing. And so this one assignment will just tell us what the puzzle is. And next time onwards, we'll try to pick up the pieces which will connect the puzzle to what the people here are doing. Okay. So mainly black hole entropy and things like that. So
we're going to kind of need a volunteer. So please, somebody step forward by the end of the lecture today, or discussion today, and we'll go from there. Okay, I'll hand it over to Bin.
So I'll stop share here.
So am I audible?
Yes.
Yeah. Okay. So I'll share my screen and show you the problem set.
Yes.
So these were the problems that were given this time. So just to remind of the first problem, and before that we'll just define the trace and the things that we are using. So the trace has a property of cyclic property, and trace AB is equal to trace BA, and then we can get something like this. Now, then we can go to the first problem. And the first problem wants us, it gives us a state, and it wants us to calculate the density matrix, find an operator whose expectation we can calculate using this density matrix, and then find the entanglement entropy. So now, so we start with the state, as the density matrix is defined as the outer product of these two states, these states. So we get the density matrix. This is the total density matrix, and then we trace out the one of the spins. We trace out the second spin. So we get this, and hence the density matrix is identity 2 cross 2 divided by 2. So this solves the first problem, first part of the problem. Now we go to the second part, and I have chosen an operator which looks like this, but a general operator in a 2 cross 2 Hermitian matrix could be as follows. So every operator can be used, every operator of this form can be, we can find the expectation value of this operator using the density matrix above. Now to calculate the entanglement entropy, that's the third part of the problem. So we take a minus of trace of rho log rho, and we calculate, and it gives us the entanglement entropy of log 2. So that shows that this state was maximally entangled, and here we are. So any questions for the first problem?
I think
okay, maybe I can make a comment on the problem. So yeah, the solution was perfect. I think the only comment I wanted to make was that in this case, you can see the density matrix on system 1 just came out to be the identity. Right? It's a 2 by 2 identity because that system has 2 states. So it's a 2 by 2 identity. So actually, very commonly, you come to something which is the identity or very close to the identity for the following reason. If your system is small, like this one just had 2 spins, and suppose it entangled with some system which is big, let's say the rest of this room, then typically the full state can be written as, you can always write any state as upspin times some state psi 1 in the room times plus downspin times some other state psi 2 in the room. And generically psi 1 and psi 2 will be orthogonal because there are so many states in the room. There's almost no chance they're going to be the same. And also by probability, the norms of psi 1 and psi 2 will be equal because again, if you go through all the possible states, if I made the norm of psi1 very small, it's like there are more possibilities if the norms are closer to equal. So the moment you have upspin times some psi1 plus downspin times some psi2, and if psi1 and psi2 are orthogonal and equal in norm, it doesn't matter what they are, the reduced density matrix on my spin is going to be the 2 by 2 identity. So whenever you take a small system out of a big system and ask for what is its density matrix, if the guy is in a very generic state, his density matrix will be the identity. So it just means that it's a maximally entangled guy, and maximally entangled means you take the upspin and you tensor it with something, and you take downspin and you tensor with something orthogonal. The only way to not get the identity is that if these two vectors you tensored with, psi1 and psi2, were either not orthogonal or one was bigger than the other. But generically, they'll try to be as close to each other as possible in length, and they'll try to be orthogonal to each other just on grounds of probability. And this is exactly what Don Page calculated. So this part is obvious. Everybody knew the density matrix would be close to identity. What Don Page calculated was the fact that if the system size is m and the total system is n, I mean, the other system is not all that much bigger, this is m and n. When m comes close to n by 2, like you start reaching the halfway point, then how far do you deviate from the identity? So that's an interesting calculation. But it's certainly true that when one system is much smaller than the other, then the density matrix of a smaller system is always very close to identity. What Page found was the corrections. And the corrections only come when the two systems are very close to the halfway point.
So, Samir, I have to ask, maybe this will come up later. I mean, much is made by a lot of these people who talk about entanglement to say, well, these matrices have an e to the s entries, and if all the entries are tiny, like e to the minus s, you can make a mistake by assuming they're very, very close to being zero, because when you add them all up, they contribute substantially to the entanglement. So is that argument disingenuous, where you simply say, that it's
That's
always
a very
going to be...
important question, because it's a very important question because that is the main reason that most people, at least in the string community, were not taking the information problem sufficiently seriously in most of the time till fairly recently. And the reason was that they were all thinking that some small correction of the kind that you mentioned, coming from some small quantum gravity effect, will basically purify the matrix, and you actually won't have the entanglement. And that's the purpose of the small correction theorem, which is problem 9 over here, that when you actually take the pairs as they are created, and then you make any small correction to those pairs, it is not actually going to remove your entanglement. So you have to actually go through the physical process that you are creating pairs one by one, and you have to assume that the particles which are created, once they have gone, let's say outside some distance like 10m or 100m, they're not going to change any further. But in the process of creation, of course, you can tamper with Hawking's leading order state and change it. Okay? And as you can see from the statement of problem 9, the changes we have made are the changes which are going to happen if the metric around the horizon suffers any small corrections. But the point is that the fact that those small corrections are not going to remove your entanglement, it is highly non-obvious. And that's what needs the power of the strong subadditivity, which is a very non-trivial theorem in quantum entanglement theory. But that will come to when we come to problem 9. But the issue is very important, because if you start adding random small entries in various places, that doesn't correspond to a process which is small correction to a pair creation process. So you have to connect back to the physical problem that in the black hole, the semi-classical horizon, you are forced to get the pair creation. You are allowed to add small corrections to it, of course, because there can always be small corrections from quantum gravity effects. Let's say e to the minus s, or even 1 upon m, not e to the minus m, but just 1 upon m. Let's even allow that. It still wouldn't help you. But seeing that is not obvious, because the number of particles coming out is m squared, m upon m Planck whole squared. And if the correction, let's say order, m Planck over m, you might think, okay, now anything could happen. But the fact it doesn't happen is what is a small correction theorem. So that we'll have to see if we can get to that today. But does that answer what you were asking?
Yes, it does. I think I was getting ahead of myself. So let's just hold off until we get to problem 9.
Okay, but that's a very crucial issue. Absolutely.
Okay, then let's proceed to problem 2. So the problem 2 is, you can think of it as an array of 15 spins, where subsystem A has 5 spins and the subsystem B has 10 spins. And we are asked to write different types of states, which gives us different types of entanglement entropy between A and B. So the first state is an unentangled state. So first of all, I'll just mention the general state as Professor Mathur just mentioned. So general state would be something like this, where 2 to the power 5 is NA, is the Hilbert size of the Hilbert space of subsystem A, and 2 to the power 10 is the subsystem B. And a general state would look like this, and IA and JB are the eigenstates of A and B respectively. So an unentangled state would be where we can factorize this Cij into AI and Bj. And so an unentangled state would lead to something like this. And this would give us an entanglement entropy of 0. And for an state where we have to find an entanglement entropy of log 2, we just take any two spins of the first subsystem and the second subsystem, and like from the idea of problem 1, we can write something like this. And as we can see, just like in problem 1, we can find an entanglement entropy of log 2. Now coming to the maximally entangled state, we, as Professor Mathur just mentioned, we just need to look at the smaller subsystem of the two, and we can take A is the smaller subsystem with Hilbert space of size 2 to the power 5, and we can write a state like this. And when we go on to calculate, we get something as log n, where n is 2 to the power 5 over here. So hence we get 5 log 2. So this was problem 2. So any questions?
That's great. Thank you. Seriously, any questions, guys?
Okay, so let me just make a comment on the significance of this. As Mathur was just saying, if one system is smaller, then the maximum entanglement entropy you can get between A and B is the size of the smaller system. So the smaller system has 5 bits. A bit is something which has 2 states up and down. That's 5 bits. Then the maximum entanglement entropy can be 5 log 2. Okay, so since each of the states of system, the smaller system, system A, will be tensored with some orthogonal state in system B, but after you've exhausted all the system states in system A, the other states in system B will not even be involved. So what people are calling these days the island formula for the entropy or so on is actually just a circular argument using this. So what they're saying is that if you have many papers would be doing this, they'll have a system A and a system B, and they will say that you should take the minimum of the entanglement of the size of system A and system B. So what you can see from here is that if you have any system, just 2 pieces of coal, their entanglement will be at most the size of the smaller system. So if you see any formula in the island community which says entanglement entropy on the left side, but a minimum of something on the right side, then actually it is simply basically going and saying that you have 2 ordinary systems, they are entangled, have nothing to do with the physics of the black hole. They're simply saying the entanglement entropy of the 2, if you take it to be the smaller of the 2 systems, you will get a graph which first goes up and then comes down. Because you can't actually, so if you take some big system of size capital N, and then you look at a subsystem of size m equals 1, m equals 2, up to capital N equals 2, and then bigger than that all the way up to capital N. In the beginning, the entanglement will keep rising, but after the halfway point, it will keep going down. So that's exactly what Page did. That's the Page curve. Page curve is for a box of gas or a piece of coal, has nothing to do with black holes. Just for any system of total size n, if you partition it into size m and n minus m, then what's the entanglement entropy? That was Page's question. It is obviously in the beginning be going like linearly, exactly like you said, by the size of m log 2. And in the second half, it will be n minus m log 2, because that's the smaller system. And this part was obvious to everybody. What Page did was he computed what is the actual turnover at the top. When you are near the halfway point, it's slightly rounded off, and the rounding off size is very interesting. It's equal to the answer you get from this maximal entanglement, whatever you get from this formula, minus m over 2n, where m is the size of smaller system, n the size of the bigger system. So m over 2n was the Page's contribution. So if you just take this answer, then it's going linearly like this, and then linearly down on the other side, a slight rounding off, which says the answer will be a little less than the maximum entanglement. The little less is minus m over 2m. That's the subtraction, making it a little less. And that was actually Page's calculation. It's also, it's a lengthy calculation, but all elementary. You simply write this entangled state between 2 systems, psi I tensor chi j, and then you say psi I will be an arbitrary state uniformly summed over the first system, chi j will be an arbitrary state uniformly summed, averaged over the second system, and then you get what you get. So it was just averaging this entanglement entropy formula, and that was Page's theory.
Why is the calculation of it being a little bit less interesting, or is it just?
It's not. It's absolutely, it has nothing to do with the
Okay,
black hole.
good.
It has nothing to do with the black hole puzzle. Absolutely not. It is interesting because nobody had done that before. I mean, it's still interesting to know that what the smoothness is at the top. It has nothing to do with the black hole problem. The fact it goes up like this, comes down like this, it's called the Page curve because Page did compute that, the only part which was not obvious. But it had nothing to do with the black hole puzzle. You could equally well say this and this, and you still have the black hole puzzle because the actual black hole is going like this. So there's nothing to do with the black hole puzzle. Okay, that's all I wanted to say. Does anybody have any other questions? Otherwise, back to Mathur. Okay, so you can pick up again, Mathur.
So yeah, Ben would like to present the third problem.
Okay, so maybe I will take the third problem. Oh, can you hear me properly?
Oh yeah, fine, no problem.
Okay. So the third problem is if we have a two spin A and B, and if we can only measure the two experiment for spin A, can we find out if A is in a pure state or in a mixed state? So it's very similar to a black hole problem. The A is very similar to the radiation, and the B is the inferring part of the pair. So first, let's look at this Stern-Gallagher experiment. So if we look at the spin A, so the general density matrix is a Hermitian matrix and the chase is 1. So we can use 3 parameters to parameterize this density matrix. And this sigma are the Pauli matrix and alpha are all real numbers. And notice that there's no prefactor in the identity because the chase is 1. If we use Stern-Gallagher experiment, so we can split the spin or magnetic momentum depends on the spin up and spin down in a particular direction. If we take this direction as the z direction, and we can do this measurement many times. For example, if we get spin up, we call it 1, spin down -1, and then we average the result. So we can get the average of the spin around z direction. And if we, the definition of this expectation value is trace of this operator with the density matrix. And if we put density matrix here, you can see the sigma z is traceless, so, and is also orthogonal to sigma x and sigma y. So the only term you can see is the sigma z, so you will get the prefactor alpha z. And then you can do the similar experiment by changing the direction of the experiment. You can get alpha z and alpha y. So in that way, you can get the density matrix if you can measure many times. The idea is you cannot measure the density matrix in just one experiment. You should do that experiment many times. And after you have the density matrix, you can decide, you can compute the entropy or compute the purity to see if it is a mixed state or pure state. And usually people will call a similar thing called quantum tomography. So you measure density matrix first and put that into a classical computer, and you can find if the entropy is 0 or non-zero. Okay, is there any question here? Okay. There's another method that might be related to island people idea. So let's consider the purity. Oh, here, notice that at each measurement, we only need just 1 copy of the state. We don't need 2 copies. But here, we can start with 2 copies. So we have this 2 copy at hand. And then we can first use a quantum computer, do some operations for these 2 copies, and then do a measurement. And do this process many times, we can get the average. And then that's the trace rho square. Then we can find if the state is pure. for more details about this method, you can look at, for example, this paper. But idea here is each time we do the measurement or do the quantum operations, we need 2 copies. Okay, so that's this. Is there any questions for this question?
So I'm not sure I understood the relevance of this. I understand that you want to calculate trace rho squared. So what is this business about doing operations on 2 copies? Do you do operations on both copies, 1 copy? I'm not sure I understood the relevance of this.
If I understand correctly, if you want to compute this one, you have use some operation that swap the bits or something between these 2. So you can now do separately for each of them. You have to have an operation acting on 2 copies at the same time.
Okay, maybe I can comment a little bit on that also. Actually, if you can go to the top, I can comment a little bit on the entire question. Let me just make it easier to go at one go in the whole thing. So can I share my screen again? So then you may have to stop.
I think since you're a host or co-host, you can just take it over.
Okay.
Yeah, you can directly share it.
Okay. Okay, so yeah, everything that Ben said is absolutely fine. I just wanted to say it maybe in slightly different words, which may make it simpler, just to give the physics without going again through the math, which Ben did. So the question was, suppose I just give you a spin. It could be up or it could be down. And you just have a spin in a box. Of course, you have many copies of it, all prepared the same way, but you have a spin in a box. And somebody asks you, is this in a pure state or entangled state? And the question was, how would you tell? Does the question make sense? What experiment would you do to actually know that? And it's always best to, in all these games, is to go through an example, and then the idea is clear, and then you can always do the math and put it on later. So suppose the spin was in a pure state would be a spinner like alpha and beta, and then that would be made of with the constraint alpha mod square plus beta mod square equal to 1. And so if you have a spinner like that, for example, you could have 1 by root 2 times 1, 1. Okay, that's the particular spinner. And what this corresponds to is that it's an eigenstate of sigma x. So if I take my Stern-Gerlach and I orient it in the z direction, so let's call it, this is a z direction Stern-Gerlach, z direction Stern-Gerlach. Then if I take this particular state, I will find 50% of the time I will get spin up and 50% of the time I will get spin down. Okay, but if I orient my spin by Stern-Gerlach in the x direction, so x direction Stern-Gerlach, then what will happen, because this is an eigenstate of sigma x, I will get 100% of this one and 0% of the other way, right? So 0% the other way. So if you have a pure state, you simply have to go with your Stern-Gerlach, try various directions, till in some direction you find you're getting 100%, and that's it. You know it's a pure state in that particular direction. Now suppose the guy was entangled, so it was up of spin 1 times down of spin 2 minus down of spin 1 times up of spin 2, and I'll normalize it also. Suppose it was like this. And you only have access to spin 1, spin 2 is somewhere else far away in a different planet. But it is entangled. And now if you take spin 1 and you measure with Stern-Gerlach in the z direction Stern-Gerlach, then you will get 50% of the time you will get up and 50% of the time you will get down. But again, even if you try the x direction Stern-Gerlach or any other direction Stern-Gerlach, you will again get 50% of the time going this way and 50% of the time going the other way. So if you have, let's say, maximally entangled, doesn't matter where you put the Stern-Gerlach, you will always get 50-50. If it is a pure state, if you take the wrong direction, like a z direction, you will get 50-50. But as you play around in a little while, you will find, aha, the x direction, it doesn't matter which copy I try, I have so many copies to play with, I'll always get 100-0. So that's how you tell if something is pure or mixed. And if it was partly mixed, like it is a lot of, let's say, 0.9 times up down plus 0.1 times down up, 1, 2, to something like that. Then if you took the correct direction of Stern-Gerlach, you'll find 90% of the time it's working in one direction and only a small percent in the other direction. So you can tell how much mixed something is by just playing with many copies. So the importance of this problem was that sometimes when people look at the radiation that comes out of a black hole. So you have many, many particles which have come out. What you're supposed to do is you can take those particles. Let's say you have 100 particles which have come out. You pass them through a complicated Stern-Gerlach with 100, different magnetic fields or whatever, and you can find out if it is pure or mixed. It's not something which is difficult to find out. You can repeat the black hole the same way, like make it the same way, let it evaporate the same way, and then you can find what is the state and whether it's pure or mixed. Now, there have been some papers, I think this thing was earlier started by maybe ideas of Susskind, and then there's Hayden Harlow and so on. They keep saying it is so complicated to analyze this that you can't actually analyze it because there are so many particles. Okay, but that has nothing to do with the black hole problem. Anything has lots of particles. For example, if you take a black hole of, let's say, mass 100 Planck masses, this is the mass of the black hole. That's already a big black hole because the only scale is Planck mass. If you had 100 Planck mass, it's a big black hole. It will emit 10 to the 4 spin particles, right? So let's say 10 to the 4 spins. Now it's your job to actually make a complicated Stern-Gerlach and check if that is pure or not, but it has 10 to the 4 spins. It's not very complicated. People keep using the word, it's very complicated. It's not very complicated. The number of particles coming out of a piece of coal is by contrast 10 to the power 23. Okay, so you'll get that many particles out of something which is a 10 to the power 10 solar mass, so 10 to the power 10 Planck mass black hole, which should definitely show you all the black hole physics you want to see. So using the fact that this is very complicated, people say it's very complicated, so we'll only look at 1 or 2 of them. That's the kind of thing that Papadimas, Raju, and so on keep doing. They will say, this is so complicated, we look at only 1 or 2 of them. On those, the density matrix looks, as we said, if you take a small subsystem out of a big system, it will always look like the entity, which will look like the density matrix of a piece of coal. And so then they will say, this whole thing is a piece of coal. But that is obviously completely nonsensical. If you look at only simple operators like one-point operators, which they keep looking at, then it doesn't tell you anything. Looking at one-point operators is not the problem. You have to look at the entire system. So what are people like Hayden Harlow and so on trying to do? What they're saying is, okay, it's very complicated to measure this. So measuring it will take time. In that much time, the black hole would have evaporated. Okay, that's a fact. So you can't go in the black hole and check and so on. But that's has nothing to do with the black hole puzzle again, because if you want to see if the black hole left you with a pure state, let the black hole go away or become a remnant. You can take these particles, you can go home, take a million years more to just analyze them, and you'll find out if they were pure or mixed. So a lot of these things you see people doing with this entanglement entropy has really no bearing on the black hole puzzle. People are just like having fun or looking at things which are not actually relevant. But I just want to emphasize the fact that there's a well-defined procedure for checking whether a stage which you have in your hand is pure or mixed. The last part which Ben was saying was, what is the point of computing rho square if you have a pure state which is of the form psi times chi? So, sorry, psi from system A times chi from system B. Then the density matrix of that will just be psi from system A, psi from system A. And so the density matrix written in terms of the basis of states in some basis will just look like this for system A. This is rho of A. So if you take this rho and you square it, rho A square, it will also look like 1, 0, 0, 0. And so trace of rho always has to be 1 because that's the property of the density matrix. But in this case, trace of rho A square will also be 1. On the other hand, if rho A was a mixed state, so it was, let's say, half and half, the trace of rho always has to be 1. So it could be something like this. Then if you compute rho A square, its entries will be 1 quarter, 1 quarter. And so trace of rho A square will be less than 1. This is what they call the purity. If the trace of the square is equal to 1, it's pure. The trace is less than 1, it's obviously mixed. Okay, so no big deal about that. And so if you want to just check if something is mixed, instead of taking the Stern-Gerlach and doing it a million times like we were doing before, you could take, as you said, we have many copies of the spin, right? So we were working with them one by one and playing with them, but we can take, let's say, 2 copies at one go. Take 2 of the copies. People are giving you many copies anyway. Take 2 of the copies, and then you can do various manipulations on them to directly get the matrix trace rho square out of it. Okay, and then again you can check if it is pure or mixed. It's just a different way of doing the Stern-Gerlach. Either you can do it to each of the spins one by one, or you can take 2 copies in your hand, sort of swap them around and do some things, and then apply a Stern-Gerlach on 2 bits to that and find out the answer in an equivalent way. So these are all just ways of checking if a spin is pure, if a state is pure or not. But the black hole problem is just to ask whether it's pure or not. It doesn't have anything to do with looking at only a small subset of them. or simple operators. They actually can't tell you anything by definition, because simple operator, whether it's a box of gas, pure state, mixed state, will always give you the answer. The entanglement of that is close to the identity matrix. So that has no information. And whether it takes you very long to analyze that also has nothing to do with the black hole problem. But people have just been having fun with trying to compute how long it takes you to do the Stern-Gerlach to find out something's pure. Okay, that's what I was going to say about it. Did anybody have any questions for me?
Samir, I had a small question.
Yes.
In all of these situations where you're trying to find the state, you need copies of the state.
Yes.
So do you want to say something about what are the challenges in having a system and then making copies of it so that you can determine its density of state?
So let me see if I understand the question. First, let's talk about something which has nothing to do with a black hole. Let's say just even a piece of coal, right? And I let it evaporate to some fraction. I want to check if the photons I have, are they in a pure state or not? So I would have to make the coal in the same way each time. And of course, the Hamiltonian of the world doesn't change. So it will evaporate the same way each time. But yes, I have to make the coal in the same way each time. And for the black hole also, then if I make it by collapsing a star, I just start with the same star each time. Now, of course, that's maybe a complicated thing in the lab to practically do. But in principle, of course, there's nothing wrong with that, right? I can start with any number of copies of the state which are identical. Notice that we don't have to let the black hole evaporate completely. So any new physics coming at the final evaporation point, that is not involved. As we have seen before, that the entire evaporation problem can be seen by just looking at some time when the slice is becoming long and long, and you get entangled pairs of quanta here and here, here and here. We'll see this in later assignments in more detail, who is entangled with who. But we saw that a little bit in the, so we have many quanta here, and they're entangled with their partners here. So this state which you get on this slice, where let's say 3 particles have been created, this is entangled with this is entangled with this is entangled with this. This state on this slice will be the same in each of the copies. So it is assumed that if you draw the entire Penrose diagram, we draw it as a Penrose diagram, and you're making it by collapsing, let's say, a shell. If I take the shell in the same state each time, then if I look at the initial state on this slice to be the vacuum, and then I evolve like this, and on this state, which is a late time state, I have my entangled pairs. The state of this state on this complete slice, I'm assuming is the same state each time I do this game with the same input shell, right? So in that way, it's just like a question of a piece of coal, because I'm still on a complete Cauchy slice, no singularity, nothing. If you can do it for a piece of coal, you can do it for a black hole. So I didn't maybe completely understand your question. So could you please ask again?
Yeah, I think I just wanted a clarification whether you're thinking about whether, as you said, it doesn't matter if it's a black hole or not, just the general question of whether you're preparing the state in the same way, or actually are you thinking of getting a certain realization of the density matrix, and through a quantum computer you do some cloning of the state, which then affects can affect the state itself. So as I understand it, you're saying, oh, just prepare, whatever, 1,000 versions of the same initial value problem.
Absolutely, absolutely. I'm not trying to clone the state. You have to do the experiment multiple times. So that's the black hole setup puzzle. Yet, if you want to measure whether something is pure or not, you have to actually, the puzzle comes, of course, just once, because you make the black hole, you get something, it's entangled, but there's nothing it's entangled with. The puzzle is already there. But if you ask somebody, how do you know this guy came out entangled or not? Indeed, you have to make the black hole with the same star 1,000 times, check the output, and you'll say, aha, I have a problem.
Yeah, thank you.
I wanted to ask a related question. So is there a quantum non-demolition version of this procedure where you don't have to repeat the same measurement a whole bunch of times on identically prepared systems, but you sort of don't destroy the state in the process of measuring it?
I see. So it's a good question. I don't actually know. Let's just talk about 2 spins which are entangled. Okay. So I just have one spin, you have one spin, and they could be in a factored state, let's say up times down, or there could be an entangled state like up, down, minus, down, up. And I don't know whether my spin is in the factored or entangled state. What would I do? Because if I don't make any measurement, I can't tell, right? So I think with the simple case, I don't see how to do it unless I have several copies. And in each time I'm actually passing through a Stern-Gerlach, which is equal to demolishing that copy, right? Because the Stern-Gerlach changes the state. How would you do it for two spins which are entangled? I'm not actually sure.
Isn't quantum non-demolition all about complementary observables? You can measure something without disturbing another, and by their nature, what Samir is talking about are things that are actually, not complementary at all.
Yes, maybe I don't understand what you had in mind by the non-demolition measurements. I know this whole thing called
Is there a way of determining what density matrix you have without sort of destroying the state of the black hole? They're not destroying the state. Basically, what you're doing is you're correlating it with another large system.
So you're not changing the black hole interior, you're only changing the radiation quanta in your hand, right? Just like you were doing with the two spins.
Yeah.
I'm just playing with my spin. I'm certainly not affecting your spin. So we're not changing the black hole interior in any way, but just given my spin, how do I tell if it is entangled with the black hole or not, or entangled with your spin or not? I think that will make me change the state of my spin.
Yeah.
I think it should
Yeah,
not be,
yeah.
Because if it was, I think you can devise some perverted experiment that leads to violation of Bell inequality type of thing. I think you'll have to change the state, I think, in a destructive way, essentially. There's a toy experiment. I'm trying to remember the details, which goes along what you're suggesting, which you can use to basically generate some violations of quantum mechanics if you are able to not destroy the state while making the measurements.
Well, that's very beautiful. If you could send a link to that, I would also be happy to see that concretely. Yeah.
I'll try to find it out.
So here the only point I was making was that all this had nothing to do with the black hole per se. All this part we're talking about in today's assignment is all true just for bits. It's just quantum mechanics. And so whatever you would do for radiation from a piece of coal or two entangled spins is all that will happen to black hole and radiation. Because you're just on a big Cauchy slice. The whole point is that you're on a good slice all through. So the inside and the outside are just two parts of a system, like two halves of a piece of gas. So no black hole physics or singularity physics or anything has come in. So all the questions are also normal questions. So
maybe I can. Oh, can I add a small point?
Yeah.
Okay. Oh, the two methods, one with using the Stern-Gerlach to measure the density matrix, the other one use two copy, exactly equivalent if you have a two quantum system. But if I understand correctly, in the Euclidean path integral, the first one is they are not be able to reproduce the result from first one, but it's easy to reproduce result for the second one. So that's the reason to think about this two different measurement, even though they are equivalent. Okay.
Yeah, I would say one thing that all these things on the Euclidean path integral they have done with multiple copies, it's actually quite meaningless, but we'll come to that when we come to the next thing on the Euclidean sections. You can't do a Euclidean measurement. Like the whole reason these people are getting confused, they keep going Euclidean. And the entire island thing is just based on the following confusion. If you accept the Gibbons-Hawking answer for the Euclidean entropy, which is just A by 4G, there's nothing more to say. You cannot entangle with the system by more than A by 4G. So their answer is that you cannot entangle with something by more than A by 4G. So there cannot be an information puzzle. But their input, if you go back to see how they're coming to that conclusion, it's actually Euclidean. So they're actually saying, I'll measure the entropy by Euclidean, assume that is the entropy, and then there is nothing to say. So we have to sort of go through their papers from the next assignment onwards and see where the circular piece is coming in. So which we will do, but you cannot actually measure Euclidean. If I actually give you a state, which is what this problem was, and I say, check if this is entangled or not, you say, I will make 2 Euclidean copies. It doesn't mean anything. So they have gotten very confused with using the, this replica trick and so on. Those are tricks that give you the value of a path integral. But even if you don't use the trick, you put the whole thing in a computer. If you ask, what are you computing? If you use replicas and saddle points and all that, don't have to do any of that. If you just want to compute the answer, as long as you're computing a Euclidean answer, you'll come out with the Gibbons-Hawking answer. And if you assume that's the correct entropy, there's no problem anyway. So in the end, you'll find they're just going in the same circle. But that's why I'm saying, let's not do the Euclidean one right now. There are people who have done Lorentzian versions of computing trace rho square. But there, if you go back, you see that they're doing non-unitary evolution. You can specifically see that they're having loss of unitarity. So it's not obvious in their papers, but when you go and see what they're doing, you will see a loss of unitarity. So it's just very dangerous to jump to Euclidean right now, because for Euclidean, they will jump to Lorentzian. Euclidean is a circular argument, the Lorentzian is a wrong argument. So it's not going to be clear right now. Are there other questions at this stage, or should we just move on to the next problem?
I think we should move on.
Okay, so I'll stop my share.
Yeah, I just wanted to say there's a question in the chat.
So it says
It has to do with
Okay,
quantum
measuring is a
non-definition,
functional.
but perhaps we should just, since in the interest of time, I think, since we've been at this an hour, we should move on to the next.
Yeah.
Okay, I'll share my screen.
Yeah, so you can share it. I have already unshared.
Yes. Sure. So the next problem is kind of a smaller version of the upcoming problem. So this is a thermopile double state, and we wish to find C that can be found using normalizing psi. And we need to show that this is a density matrix, is the thermal density matrix at temperature T. So we go through it like this. So we write psi, and by normalizing, I find C square is equal to this. And now we take the reduced density matrix by tracing it over B for En primes, and we find that the density matrix that we get is C square, summation e to the power minus Ek by T, outer product of Ek eigenstates of state A, which is the thermal density matrix. So we can kind of move ahead in this problem and come back to this when we discuss problem 6. So any questions?
Okay, but then I'll just make a small comment. So the solution is, of course, completely correct. What this is used for is that when people are trying to do StatMech, like you want to take a density matrix for the gas in this room. Now, we know we want to take a generic state. So the generic state will be maximally entangled with the heat bath. So all that is true. But if you actually want to take a concrete example of something which is maximally entangled with the heat bath, well, this is what you would write. You would put e to the minus energy upon 2t. The 2 is there because the next stage you'll be squaring it together density matrix. Then it will become e to the minus e over t, which is what you want. So if you take e to the minus e over 2t, take the nth energy state in my room, tensor with the nth energy state of an identical copy in the other room. And then if you say, take this maximally entangled state with this weight, and then if you trace out the other room, you're left with the thermal density matrix on the copy in my room. So there's just just a practical way of writing down a state, which is overall, of course, pure between systems A and B, but which when reduced to system A, which is the system of my interest, it is a thermal density matrix. So just a mathematical trick. It's a convenient trick, but it has no physics of its own at this stage. Yeah.
We can go ahead with problem 5. Bin wanted to take this. Yeah, Bin, you can go ahead.
Or maybe Samir, you can explain the question 5, because that's based on like paper.
Okay, yeah, so I can do that maybe. So I'll just share my screen again. And okay, so what is happening in a lot of these problems is that people are very confused about how the black hole differs from a piece of coal. So what is happening in this whole island part of the game? So let us be very clear, what is a piece of coal and how does a piece of coal actually follow the page curve? We just saw that the black hole doesn't follow the page curve because you keep creating these entangled pairs and each new particle is entangled with another particle inside. So after n steps, the entanglement will become n log 2, as you will see in a later problem. So the entanglement keeps growing. So how does a piece of coal behave? That the entanglement first grows and then comes down. So we can just make a toy model of a piece of coal. So let's say we have, 10 atoms in the coal, and each atom can emit a photon, and there's the photon going out. So in the beginning, the atom keeps emitting a photon, and when the photon goes out, typically the photon will be entangled with the atom left behind. So if the photon is spin up, the atom will be, so this is for the photon, then the atom will be left and spin down. And then it could also be the other way because the photon could be spin down and the atom could be spin up. So if the overall state was a singlet of the atom before it started, when it emits a spin one particle, it will get a negative spin left behind. So typically when an atom actually emits a photon, the two get entangled. So this is a toy example of how the entanglement between the radiation and the atom is sort of growing, because when the next atom radiates something, the entanglement will grow further. So if I put emissions here or time on the x-axis, and I put the entanglement entropy Sn here, after every emission, it goes up by log 2. So this is log 2, and then after 2 steps, it's 2 log 2, and so on. So it's keeping on growing. So now after all these 10 atoms have emitted a photon, now there are no more photons to emit, but I want it to model complete evaporation. I want nothing left for the piece of coal. If I'm left with something, it's like an eternal hole, right? It sort of comes down to a charge at maximal hole, and then it won't radiate any further. I'm looking for a shorter hole which completely goes away. So if I'm looking at that, then let me also model that when I'm left with this thing behind, I'll call it ash, and then these atoms can also fly out, right? So then the atoms will also fly out. And so then what will happen is, in the beginning, I just had some photons coming out, but later I'll also have the atoms flying out. And so in the end, there's nothing left here. So there's nothing here where the coal was, and the atoms come out one by one. But you can see that if this is the complete radiation, this quanta is entangled with this one, this quanta is entangled with this one, and so on. So the radiation is overall in a pure state, but every part of the radiation is entangled with something else. So that's my simplest model for a piece of coal, that in the beginning, the entanglement of the radiation with the coal goes up, but as more and more pieces of these atoms start coming out, the ash starts coming out, there's less and less left behind. When this piece of the ash has come out, then this and this are entangled with each other, but they're not entangled with what's left behind in the coal. So then the entanglement will start going down. So it'll go up like this, and then it'll go down like this. So in this simple model, we'll simply get a page curve that goes up and comes down. Now, of course, this is not a generic model. What can happen is every time an atom emits something, then interaction on the piece of coal reshuffle all the bits a little bit, right? It's not that the atom will stay where it is, and then the next emission happens and it'll reshuffle or something. And then when the ash is coming out, also one atom comes out, then they can reshuffle. So reshuffle means that they can exchange spins and so on. So in this paper, which I referred to there, we made lots of different models of this where we reshuffle them. You can make lots of toy models of reshuffling. In each case, you find the graph is sort of like this, just on general grounds. It'll sort of go up and come down. If you take something very non-generic, it can do absolutely anything crazy, obviously. But in general, it seems to roughly go up and roughly come down, but that's just based on generic properties. So if you just keep this model of the coal in mind, it always tells you how a piece of coal behaves. But what was important here was that the particle which was inside, the atom which was left behind when the photon went out, that atom also comes out. Now, what is different in the black hole is, if we draw the black hole again with its long slices, this guy is entangled with this guy. So we had called as B1, and this is C1, and this is B2, and this is C2. So B1 is entangled with C1, B2 is entangled with C2. But what happens is, even at the end of evaporation, the C's don't come out. If the C's came out, it would be just like the piece of coal. So then you can ask, how is the black hole decreasing in mass if the C's are not coming out? And that's the whole point about the black hole, that the particles inside have negative energy. So the initial mass of the shell, let's call this the shell, which made the black hole, is still there. That has a mass m. These have negative energy. And so this negative energy plus the energy of the shell together make 0. So the mass of the black hole is going to 0, but the stuff you're entangled with is not coming out. And so how can there be so much stuff inside the mass m and also all this stuff, and still the total mass goes to 0? Well, that's all because the negative potential of gravity. So because gravity has a minus g mm over r, if you put things close enough, which namely means you put them inside the horizon, then the negative minus g mm over r overwhelms the mc squared, and the net mass can be 0. So without with still having a lot of stuff in there. So that's the essence of the black hole problem. Because the gravitational potential is negative, you can have particles of negative energy inside the horizon. And to see that that happens at the horizon scale, if you have a test object of mass m, it has an energy mc squared. But then if you put it near a black hole of mass m at some distance r, then I'll take minus g m over r. And then I can ask, at what r will this become 0? When does he start getting negative energy? You can see if little r becomes small enough, then it can start getting negative, because this guy has a negative sign. And so the little m cancels. And you can see this happens when r is equal to gm over c squared. So this is Newtonian. Of course, when you do it with gr, it becomes 2gm over c squared. But you can see when you go inside the horizon, that's when the negative gravitational attraction actually gives you negative mass. So a black hole behaves with negative energies. So a black hole behaves very differently from a piece of coal. You always get the entanglement keeping on going up, and yet the mass is going to 0 because of the gravitational potential energy being negative. In a piece of coal, there's no negative energy anywhere. And what's happening is the C's are also coming out. And that's what this toy model was. So this is the whole difference. As long as you have a smooth horizon, you actually cannot get out of the information puzzle. The entanglement will keep growing. If you want the stuff inside to come out, then you have to do something to the black hole, because in the black hole, as you know, the light cones point inward. So here the light cones point this way inside the black hole. At the horizon itself, they are completely tangent to the horizon. So once nothing inside can actually come out. So either you're going to do some kind of non-local transport, get it out through a wormhole, which is what the wormhole people would like to do, or the stuff doesn't come out. And so if you want to solve it without having a wormhole, then you just can't have a horizon, which is what the fuzzballs do. Then it's like a piece of coal. Whatever goes out, if it leaves something behind, like in the atom, that atom can also come out. But then there can't be a horizon, because with a horizon, it couldn't have come out. So indeed, that was the idea of referring you to make models of a piece of coal, because whenever any island people is saying, I have done this or I have done that, what you have to go and ask him is, okay, you say you have a smooth horizon. If he says yes, then you say, okay, what happened to the particle which fell in? With a smooth horizon, you have to have particle creation. And if the particle fell in, where is it? You're entangled with it. How does it come out? If he says through a wormhole, you can then say, okay, I would like to examine the dynamics of wormholes or whatever. I don't believe it is correct, but then it's up to him to give the dynamics of wormholes. If he says, no, I don't have a smooth horizon, then you say, okay, then you are making a fuzzball. And your difficulty is, how do you make something stand there? Because the force at the horizon is so strong, like sucks everything in. And the fuzzballs of string theory are the only construction that prevent you from collapsing. And if they're not even looking at string theory, you're not making a fuzzball or doing all this stuff, they will always have the thing just falling in. So what is actually happening with the island people is they're not actually making a piece of coal, because that's the hard part. How do you make something which violates the no-hair theorem? They're actually saying it's a smooth horizon, and then they're not actually looking at the entangled pairs. Then they simply, at the next step, they jump to a piece of coal and they start talking about a piece of coal all through. So this is the whole circular loop that they are going into. And so we just need to understand how a piece of coal behaves and why it can't happen if there's a smooth horizon, so that we can then go and look at all the island papers one by one in later sessions and just see where each of them is making a mistake. So that's all I had to say about this problem. Let me see if there are any questions for me. Okay, if there are no questions, shall I stop my share? And
yeah, I think we should.
Yeah.
I'll go ahead with the problem 6. So this is essentially problem 4, but here we have replaced En by n omega. And here we are moving ahead with our calculation, and we are finding the entanglement entropy of oscillator 1. So as before that, we had found the reduced density matrix, and we have changed En as n omega, and with c square as this, which is summation is 1 minus e to the power minus omega t, and the entanglement entropy comes out to be this, and omega by t. And then for omega approximately equal to t, we are trying to find the entanglement entropy, which comes out to be 1.04, which has like the same order as log 2, which was asked in the problem, where we can replace by a simplified model of psi tilde of this maximally entangled state with 2 spins. So yeah, this would be, yeah, any questions and comments?
Okay, so just to comment, I mean, that sounds perfectly fine. And so the only point of this was that people got very confused with the entire long form of the Hawking formula. It has so many terms which are all like you written at the top of your line. It's a thermal density matrix. So it just looks confusing, but you lose nothing by simply modeling it as, 0, 0 plus 1, 1 or something very simple, because the entanglement entropy, the whole paradox is that it's going to keep growing and going to grow to 10 to the 70 for a solar mass black hole. Whether it's 10 to the 70 or half time 10 to the 70, it's the same puzzle. So the actual form of the Hawking radiation, people often kept arguing, is it like exactly thermal, slightly different from thermal? All that is completely irrelevant. It had nothing to do with thermal, because 0, 0 plus 1, 1 is not thermal. It's not even the exponential form or anything. You just need to know that the two particles are entangled. So it doesn't have to be thermal, like it doesn't have to be black body, because if you have radiation from the sun, it's not black. It doesn't have to be exactly black body. And the reason the black hole radiation is not exactly black body, it's the black hole has a radius which is of the same order as the Hawking radiation wavelength. So whenever a body has the same order as the Hawking radiation wavelength, it's always going to have gray body factors, because it won't be exactly thermal. So people kept worrying about the fact, if it is not exactly thermal, does that actually capture the information in some subtle way? But all those are completely irrelevant. It has nothing to do with being thermal. You can emit all your particles at just one color, let's say yellow. As long as they're entangled in the 0, 0 plus 1, 1 fashion, you still have the same problem. So the actual shape of the graph, whether it's exactly black body, it has gray body corrections, it's all completely irrelevant. So it's just the entanglement which is important, and this very simple model captures everything. So it just simplifies the logic, and one can focus on the real physics. That's all I was saying. So you can take it back.
Okay, so the last two problems. So any questions for this? Yeah, so the last two problems will be presented by Ben. So I'll stop my screen sharing. You can take over.
Okay, so the problem 7, in this problem, so we want to see if we have unitary evolution for one of the subsystems, can we change the entanglement between the system A and system B? For example, if system A and B in an entangled state, in a pure state, over a pure state, we can write like this, and we can compute for example, the reduced density matrix for system B by tracing over A. And now let's apply a unitary operator for system A only. So we get a new state. Then the reduced density matrix becomes this. So we have unitary for the cat and also the unitary for the bra. Because we trace over the system A, so we can use the cyclic property for system A and move this U dagger this side, and so we get the old density matrix. So that means a unitary matrix for one of the system cannot change the entanglement entropy between the system A and B. Okay. Oh, is there any comments or questions? Okay, so
if there are no questions, maybe I'll just comment on that. So that's important for the black hole puzzle, because people often say we don't know what happens to the quanta that fell into the black hole, right? When you have an entangled pair, one guy comes out, that's radiation, comes to flat space, that's no problem. We don't know what happens to the guy inside. But the point is, it doesn't matter what happens to the guy inside, as long as we know the physics is unitary, because the guy inside can be churned in any way you like. It doesn't change the entanglement of the radiation with what is happening inside. So right now we have said if everything is on a good slice, On the good slice, we saw B1, C1, B2, C2. So on a good slice, we actually know what is happening inside. But somebody would say, I don't believe that the good slice is correct. Maybe once the slice becomes too long, some new physics takes over. But it doesn't matter what physics takes over in the entire black hole. It could be very non-local. Inside the black hole of size m, it could be very non-local, but it doesn't affect the entanglement of the radiation which is far away with what is happening in the black hole. So that's very important, because otherwise people can always say, because new things can happen in the black hole, it actually has nothing to do with that. As long as you have a smooth horizon and you create a pair and one guy is out, what happens to the guy that falls in is no longer relevant. Right? So even though in the semi-classical approximation, you know exactly what happens to it in the good slicing, even if somebody were to say, I don't trust what happens to it deep inside the hole or deep inside this long slice, you say it doesn't matter. So that's the relevance of this. And the reason this is true is very simple, because if I have this room and that room and I have a spin and you have a spin, if I have spin up times spin down minus spin down times spin up, okay, that's maximally entangled. Now you take your spin and let's say you turn it around. So your spin up becomes spin down. Now it will be up times up minus down times down. Instead of up times down minus down times up, the entanglement remains log 2. So it doesn't matter what unitary rotation you make on the states in the other room, my spin will just get entangled with different states over there. But how many terms were there in the sum, something times something plus something times something, that doesn't change. So the entanglement doesn't change. So that's all there is to it, but it has an important implication for the black hole, because what happens deep in the black hole is irrelevant. Okay, that's what I was going to say. I'll turn it back to you.
I just wanted to ask a question. So if you don't know what happens inside the black hole, how are we sure that the evolution would be unitary?
So we are not sure. If somebody wants to say that evolution inside the black hole is not unitary, then fine, right? Because then, so suppose you still have the good slicing. So somebody could say when the slice becomes very long and have created many particles, the physics inside the black hole is not unitary. That's, for example, what Hawking said, that the whole black hole can evaporate, which means all the different states of the C quanta all map to one state, the vacuum. When two states go to one state, that's non-unitary, right? When two orthogonal states map to one state, that's non-unitary evolution. So that's the non-unitary solution. So you can always have the non-unitary solution. If you say that quantum mechanics is violated by the black hole formation and evaporation, that is an answer. I think the reason that's important to ask is because a lot of the papers these days are secretly doing that, non-unitary, but it's not obvious. Like sometimes they say we will change the inner product on the inside because of new wormhole connections in the replica. You'll see all these words. And that sounds very confusing. If you undo that and see what they have done, what they've done is they've actually got a non-unitary evolution. So when you make two replica copies, you have copy 1 and copy 2. And normally a dot product would be copy 1 with its own bra and copy 2 with its own bra. What they will do is they'll take the symmetric sum and difference, 1 plus 2 and 1 minus 2. And 1 plus 2 will dot with 1 plus 2, but 1 minus 2 will dot will go to 0. So by making a symmetric replica sum, they will take some states and they'll crush them to 0. So it's just not easy to see, but all the stuff they do, say now I have done this, it's actually equal to non-unitary evolution. That's, for example, in Mathur and Maximally papers. Okay, I'll hand it back to you.
Okay, so the next problem is to compute the leading order entropy of the Hawking radiation. Okay, so we have the state like this part, and we can compute the density matrix by product with the bra part. So we have this density matrix for the whole system, and the system B, for example, describe the radiation. So we can trace over the particles, the system C, the inside part of the inside black hole part of the partners. So by tracing over C, for example, for the first term, we will have a product between this term and this term. So we get 0, 0, and this term get 1, 1. So we can get the reduced density matrix for the radiation. And by reading this as a matrix form, the first one is half times identity, 2 by 2 identity. And the second one is the same identity, but different labels. So by taking the product, for example, the identity times identity will get a 4 by 4 identity. So you can see you will get this answer. So you can see it is a diagonalized form and with even distribution. And thus the entropy is the log, the number of identity elements diagonal elements, so 2 to the n, so we'll get n times log 2. So we can see this entropy grows with the number of pairs linearly. And in the later section, we will see how to make corrections to this state. And I will leave this for Samir.
Very nice.
Maybe I'll just make a comment on this, and then people should ask questions, because it's sort of crucial. This is what Hawking basically said. And so, and even simpler, maybe a slightly different language to see this in is that after you have emitted n quanta, then all the states possible for the B1 to Bn are all the different sets, right? 0, 1, 1, 2, 0, 1, 1, 0, 0, any set. There are 2 to the n possibilities. And the overall entangled state of all the B1 to Bn with the C1 to Cn is that whatever state you take outside, let's say 0, 0, 1, 1, 1, 0, it just has the same copy inside, 0, 0, 1, 1, 1, 0. And so it's just a sum of 2 to the n things maximally entangled. And we've already seen the entanglement entropy of something which has 2 to the n terms in the sum is going to be log of 2 to the n, which is n log 2. So it's really as simple as that. Whatever you're getting on the outside, its mirror copy is inside. So that's the maximally entangled state that Hawking is producing, and that's the page curve. And so again, if anybody presents to you a solution to the puzzle saying, I have done this or that to solve it, you simply have to ask, come back to this one and say, what are you changing? At each step, are you changing the answer at each step? If you're changing it by a large amount, you don't have a smooth horizon, because a smooth horizon is a direct calculation that you get that emission. If you change it by a large amount, you have a fuzzball. So how do you do that? If you say, no, I changed by a small amount, well, the next problem will tell you that you actually can't affect the answer. Okay? It's going to remain the same. You won't solve the puzzle. And then if he says, I'm not changing it, it's going to be something like this or close to this, but I still have a solution to the puzzle. Then you have to ask him, look, this is the density matrix. How did you get out of this? So this is what you have to bring people down to. What you'll see is that most of the island papers are not writing down the actual Hawking calculation or even addressing it, because this is the calculation you have to worry about. What they're doing is they're writing the Euclidean entropy and saying, because that is given by area upon 4G, they then assume that's the entropy of the object, but after that it's a piece of code. As we'll see in the next assignment onwards, if you assume the system has only a finite number of states and it radiates like a piece of coal, as the area goes down, you keep saying there are less and less stuff in there, but that's what happens for a piece of coal. The whole point for a black hole is, as the black hole evaporates, there's actually more and more stuff in it. Its mass is going down only because of the negative energy of gravity. So they're actually modeling a piece of coal, but they start by talking about a black hole and then they go to a piece of coal. The difference is exactly this expression which is on the screen right now, that the black hole does this, while a piece of coal doesn't do this. So you have to bring people down to this and ask them what are you doing. That's all I was going to say about it. So any questions or comments?
So is it fair to say that what the Islander people are doing is just sort of claiming by fiat to fix the problem that after sort of n over 2 bits are emitted, we just sort of declare by hand that the b sub n's for the b sub I for I bigger than n over 2 are secretly pulled from the C sub n's, I guess.
Yes, right. So that's what a piece of coal would do, right? In the beginning, the BIs are coming out as themselves, and the later BIs are not new members of pairs, but you're pulling out the old CIs, and then you're all good, right? So the island people are trying to say that, but they're saying it in ways which obscures it, because they know they cannot beat this calculation which is on the screen. That's Hawking's calculation, right? So then they're saying several different things, and the fact that those are different things is what is creating the confusion.
Sorry, a lump of coal is a little different, right? Your lump of coal always has a remnant, which is the burned out coal.
I have modeled the coal a little differently. I said the rest of the coal also floats out like ash, so nothing is left behind. That's what I meant by coal. So the first,
okay, yeah, but that then again is different, because the late radiation is different. How to say this? You're just throwing out the bits that have in the ash, sort of scattering them to the winds.
Yes.
Whereas in the Hawking calculation, you're wanting to somehow claim that the Hawking process at late times is not any different from the Hawking process at early times, but the bits that are being emitted somehow are differently constituted.
So that what you just said is exactly what you would like, but that's exactly what you can't have. Because let's see what's the meaning of differently constituted. Because what they were trying to say was that let's try to do what you're saying. First, the bits come out as B1 entangled with C1, B2 entangled with C2. And after the halfway point, you want the next B that is coming out to not be a new B, but somehow to be made out of the Cs. That's what you're wanting, right?
That's right.
I was trying to do the same for the coal. I was trying to take the ash out, but you can make your own model for a coal.
Right.
They want the new B to basically be something like the ash, and that's coming out. Now, the point is, as long as you have a smooth horizon, what Hawking would tell you is, I have the vacuum. You can see the new B and C coming out, and the new B is a new B. It is not actually made out of all the Cs. What happens to the new C that falls in? I don't know what happens to it, but I'll assume it is unitary for the moment. But then I have no choice because the C and B coming out are actually new. If you want the C and B coming out to be actually not new, but reshuffles of what was inside, you can't have a smooth horizon. Then you have to have something like a piece of coal where the ash is actually floating out. So this is exactly the issue. I'm glad you're pointing this out, because they want to have a model where the new bits coming out are in essence picking up what's inside the coal, but a smooth horizon exactly doesn't allow you that. So that is exactly the puzzle. So they're restating the puzzle and jumping to the answer, but the answer is in contradiction to what they're assuming, because they want a smooth horizon. And then with that, you actually cannot get the reconstitution. So, so exactly, that is the puzzle.
Well, so I guess the question is, how close can you come to effective field theory near the horizon? And I think this is, in some sense, what they're trying to get at. Yes. Is how close can you come to effective field theory near the horizon? You know, as it's usually understood. Yes. And so you know, what my understanding is, what your small corrections theorem is saying is that okay, if you have this sort of bit pair model, you have to say where these bit pairs are coming from, and in quantum field theory, in the usual evaporation process, they're basically being drawn up from the ultraviolet and being stretched in the vicinity of the horizon. And so what the island people are somehow saying is that these things that you're continually drawing up from the ultraviolet cutoff and stretching out to macroscopic scales are sort of not new degrees of freedom that are invented out of whole cloth. Rather, they're being constituted in some very complicated way from the early radiation.
So that's actually exactly what the small correction theorem says cannot happen. So what they're trying to do is exactly what the small correction theorem says you cannot do. So let's try to model that in a way which will, maybe I can just share my screen again, or maybe I'm already in screen share.
You're not.
So it's very important that that's what people would like, because then you can keep your smooth horizon and also like get what you want. But they have, if you try to go one step further and say, let me make a toy model of how this happens, you start thinking about it and you find why it can't happen. And the reason it doesn't work is the following. So let me again draw this picture of the horizon that this is R and this is U. And I have my thing which is stretching. This idea of pulling out the new degrees of freedom from the ultraviolet has always been confusing. So the way I actually wrote the small correction theorem is in a way which does not actually use the ultraviolet. And then actually I found that this other way of not using the UV is also in old papers of Jacobson and so on. So we'll never use the UV. The way to phrase the question is this. You actually look at any given slice, let's call it time T1, and you ask, is the state on this slice the vacuum or is it not? So we're going to ask, is the state on this slice with the vacuum, is it almost 1 minus some order epsilon, or is it not? So suppose you say, okay, right now it's the vacuum in some degrees of freedom. It could be some very complicated combination of degrees of freedom of the black hole. It's the vacuum. Okay, close to the vacuum, because small corrections are always allowed. Then what you say is, and I'm only interested in the low energy modes here. So as far as the low energy modes are concerned, modes down from, let's say, 3 kilometers down to 1 Fermi, the physics that we can see in the lab, they're all in the vacuum. Then if you follow the evolution of those modes, you'll find a pair has been created if the physics is normal. Then somebody says a new entangled pair has been created if the physics is normal. So then they say, no, the physics, whatever is happening, is not going to give me this pair. So then you ask them, okay, why don't I get that pair? If the physics here was effective field theory at lab scales between a Fermi and 3 kilometers, if you give me the vacuum here, I have no choice but to get a pair of particles here. Okay? So then they say, no, the state here wasn't the vacuum. It was something other than the vacuum. So now you don't know what's going to happen to it. Then you say, okay, so are you telling me there's a state here which is not the vacuum? And then I can just follow it, let's say from, at the Fermi scale or wherever my lower cutoff, the things will emerge from there. If you try to excite it with excitation at the Fermi scale so that those excitations can change something, then you find that the state out here will have the energy density of nuclear matter. It's completely not the vacuum. So you have to sit with this for a while and say that you'll find you're going in a circle. Either you say that I don't have the vacuum there to start with, in which case you have to say, how did you make the first ball? How is it standing there? Or if you assume it's the vacuum only on low energy modes, let's say from 1 angstrom to 3 kilometers. If it's the vacuum for those modes, I'm just close to the vacuum. Doesn't even have to be exactly the vacuum. The moment you give me that, and I go to the next slice, which is 3 kilometers above that, I just have the physics in this room, but I only follow things from 1 angstrom to 3 kilometers, or from 1 meter to 3 kilometers. That's all the part I need. The whole pair creation happens at 1 meter. They're already basically in the vacuum. They're not excited. By the time it stretches to 3 kilometers, I already have the excitation completely done. It won't stretch anymore. I only need the physics from 1 meter to 3 kilometers. And then all you have to tell me, the 1 meter modes on my initial slice, were they in the vacuum or was there an excitation in them? If it was an excitation, I'm going to ask you, how was it there? How do you break the no hair? If it was the vacuum, you don't have a choice. So that is how you actually bypass this trans-Planckian problem. And you find that anytime you try to make this precise, you're stuck.
Yeah, the question is, do you ever need to go beyond your one meter at the UV end? So you say, okay, things stretch, by the time you get up to the top of your picture, but then the modes that are at the later time slice, the modes that are at your UV cutoff had to come from somewhere, right? They're not in the effective theory on the initial time slice.
Yep.
They have to be constituted from something. And I thought what the island people were saying is that they're secretly being constituted from the early radiation. That's what the island is. It's saying the interior of the black hole has sort of been transferred. The entanglement, how to say this? The things that the Hawking quanta are entangled in any solution to the black hole information problem, the emitted the partners of the late emitting pairs have to be made from the early radiation, and in order to solve the information problem. So in some sense, is sort of in this sort of circular reasoning, that's what the island people are saying, that, oh yeah, of course, we have some excuse for why the partners of the late emitted Hawking quanta are not just some random, things that we, that are totally uncorrelated with the radiation, but they're actually made out of the early radiation, and that's how the entanglement.
I understand exactly what you're saying, and that's exactly what they're saying, and that's exactly why they're going in a circle. But look at the answer I was just giving to exactly that. That's the statement of the problem. If you could really constitute the late quanta out of the earlier ones, it's like a piece of coal. That whatever you were entangled with the partner, when the C quanta comes out, it's like the ash coming out. You were entangled with the ash, now the ash comes out. The reason you can't have that is, as I was saying, let's say on this one you had the vacuum and you looked at the 1 meter modes and you were in the vacuum. And then you found you had a pair of particles here. And now you will say, okay, what about the 1 meter modes here? I don't know anything about them. The 1 meter modes on this slice, because I'm now going to go to the next slice, right? And stretch those. The 1 meter mode here actually came from half meter modes here. And so even though I told you the 1 meter modes here were in the vacuum, I didn't actually tell you what the half meter modes were doing. So could there be some miracle happening because of the half meter modes? But I am answering that question. I'm answering it by saying, I will actually not even ask you about the half meter. All I will ask you is, again, on this slice, you tell me whether the half, again, only on the 1 meter modes, are the 1 meter modes in a vacuum or are they not? I'll only ask you about the 1 meter modes. I will not go below that. And I'm going to give the question to you and let you completely choose. The 1 meter modes, which are in a vacuum on this slice in the normal Hawking calculation, I'm going to ask you, are they in a vacuum or are they not? And you can pick. If you say they are in the vacuum, then I will say my evolution of the 1 meter modes gives me the entangled pair. At this point, you can't stop me because 1 meter, 3 kilometers, I'm supposed to use my low energy effective field. I'll get my entangled pair. So you can take the other choice. You say, no, the half meter modes here are in an excited state. I say, aha. So your state on that slice in terms of these half meter modes is not the vacuum. I already allowed you that possibility. And I'll ask you if it's not the vacuum. Okay, let's say the half meter can, you can go all the way down to your lab scale, which you know the physics at, let's say 1 Fermi. If you find all your states at 1 Fermi are not in the vacuum, that's what I was saying. You have nothing like being close to the vacuum doesn't help. For every mode, let's say the 1 meter mode, you can be in the vacuum plus the 1 quanta plus the 2 quanta with coefficients alpha, beta, and so on, right? If beta is small, it's actually you're going to find from small correction theorem doesn't help you. If beta is order 1, you get the energy density of particles of half meter. In fact, as I keep pushing a half meter down to, let's say the Fermi scale, it's like nuclear density matter. You find the horizon is not the vacuum. So then you have to ask the person, you have a state on this slice in which the lower modes, not Planck scale, but between Fermi and 1 meter, they are actually full of energy. How is that energy standing there? That's not the vacuum. So at every stage, I'm going to ask the question afresh. You will say, where did this mode come from? I say, I don't care. You pick. Wherever it came from, is it in the vacuum or is it not? I will only go from this slice to the next slice. And in this way of formulating the problem, it has nothing to do with the Planck modes.
Yeah, but in this toy model, I think I'm trying to say that these things that you're calling 1 and 0 are secretly complicated composites of things that come from string theory. You're trying to sort of like isolate one particular subsystem and declare that the unexcited thing, the vacuum of this reference quantum field that's Hawking evaporating is somehow divorced from everything that makes up the black hole.
So actually not. That's important. Let me go to that also. So we are looking at this slice, and as we said, this semi-classical slicing could be some very complicated combination of the actual black hole degrees of freedom. We are allowing them that, right? And so, but in this degree of freedom, let's say you have the 1 meter quanta, and let's say that they have assumed that they are in the vacuum state, and then still in this effective degree of freedom, those guys are going to get an entangled pair, still in terms of some effective mess, which I don't know what it is. Okay, so right now I'm giving you what you want. The problem is at the next stage, because this guy, which is the B1, which I have created, the C1 is entangled with, and I don't know what B1 and C1 are made of. They can be very complicated combination of the bits in the black hole. But now the B1 leaves. That's very important. Once the B1 leaves, this was my horizon, R equals 2m, and my B1 mess has gone out here. It's entangled with this C1 mess, and this could be made out of any degrees of freedom in the black hole, as messy as you want. But now the B1 leaves and has gone to R equals 100m. Now is when you're in trouble, because now I know what these guys are. This is like a spin which is in my hand. It's in my lab right now.
Yep.
These guys can be made in any way out of the black hole. I don't actually care how complicated. But the entanglement of this guy with this guy has gone up by log 2. So this is what I would like you to just focus on. Try to make me a model where as long as you were making these bits around the horizon, they had to make effective field theory with the vacuum on the earlier state, which is forcing you to make a pair on the next state. You have to satisfy that for effective field theory. I'm not going to ask you about trans-Planckian modes, only effective field theory from 1 meter to a meter. And then you have to add in the fact, the bit outside, up to here, there could be any complicated combination of the actual black hole degrees of freedom. The outside guy leaves. And now this outside guy which has left has to be an ordinary spin, which I can do what I want with my lab, in the lab. And this guy's entanglement doesn't matter what the C guys are made of. So if you actually try to make me a model of this, where somehow using the fact that in the black hole, everything could be made of everything, and you still had effective field theory, which could give you this entangled pair coming out just from 1 meter to 3 kilometers, you would have allowed the island guys to do what they want, because they would have said, we're not telling you how the puzzle is solved, but just there's a mess, it comes out. But in fact, that's exactly what you got. So you have to try to, the moment you try to make a model in which the bits which are out are now out, you will see the entanglement of the outside has gone up with the inside, and you actually can't reconstitute the B1 and C1 in a way that it actually reduces the entanglement. So I can understand it may not be, there's no way I can immediately convey just a couple of pictures, but if you try to make a model, just take some model and model the bits, we can focus on that, and then it will become clear why you can't do this. So let me try to push it further here, because just try to make a model where you keep the effective field theory there, keep the vacuum to leading order on the slice, and the bits after they are passed up some distance are normal bits. They can't further communicate with the black hole, and you will find you can't do that. So maybe we can talk offline about that. You could make me a model and we can drill down from there.
Yeah, I guess maybe I can ask one last question, which is, when a reasonable sized black hole is half evaporated, what's how to say this? So I'm gonna emit the n/2 + first Hawking quantum. So that has to start decreasing the black hole entropy. So it somehow has to be now entangled with the early radiation. So so I guess my question is, okay, what scale does that n/2 + first quantum have when the first quantum is being emitted? You see what I'm asking?
You mean how much? What's the
stretching? What's the stretching that the spatial slice has undergone by half evaporation?
So the stretching is the following: each time you emit one quantum, it stretches by 3 kilometers. So the total number of quanta emitted is m², which is the entropy, m/m². Mm-hmm. So you're going to emit of the order of m/m² quanta, and each one has a wavelength of order m. So the length of the slice is m³. This is the m³ scale that comes in everywhere, right?
Yeah.
So the stretching is huge. That's why it's important to phrase the problem not using Trans-Planckian physics, but only from one slice to the next.
Right, but what I'm saying is that it sounds like you're saying that this mode halfway through is some power of m smaller than the UV cutoff when I'm describing the initial stages of evaporation.
Yeah, some power of m smaller than the UV cutoff. Absolutely, absolutely.
Right. So it's not even in your description.
It's not in the description. So that's exactly right. So that's why the semi-classical physics has this issue, that's why you need to go from one slice to the next and throw out the Trans-Planckian. All these earlier formulation of Hawking, when he did the thing using the Trans-Planckian, you could always say, I don't know what is happening at Trans-Planckian physics. How do I know that a new mode comes out? But people soon got rid of that, because you can always go from one slice to the next. And if it's a vacuum on the earlier slice for the low energy modes, 1 meter, you already have the puzzle, because you'll get the entangled pair of 3 kilometers of the next slice. So that's right. The only correct way to phrase the puzzle. The old Trans-Planckian way, which was the initial paper of Hawking, completely obscures the problem.
Right.
So this is what I was mentioning on this earlier last time also, right? If you look at the cosmology, it starts from marble-sized ball and stretches to a 3000 megaparsec universe today. So if you ask, how much stretching is that? Every 1 meter mode in your lab today was actually Trans-Planckian at that time. But not at that time, but if you go sufficiently far back, it was Trans-Planckian. So we know that space actually behaves like that. That does not destroy semi-classicality. I
see. I think I understand what you're saying. That in order for me to have this late quantum actually convey information, you say, okay, suppose there's some way of recycling your C1 into a BC pair at later times. so that some piece of the information in the entanglement that's encoded in the state of C can somehow be emitted later on. And you're saying, how can I possibly put information into a later pair being emitted? The only way I can do that is if the BC pair that I create at later times has some information about the entanglement of B1C1. And that means by construction that my BNCN state is not in the vacuum.
Exactly. So if the state at the horizon is in the vacuum or close to the vacuum, the small correction theorem will tell you, you actually cannot do the encoding, which these people want, because what these people want is they are restating the piece of code. They're just restating the problem. That's what you want. But what you want is what you can't have with a smooth horizon was Hawking's original calculation. The small correction theorem tells you that small corrections won't help you. And so if you keep the smooth horizon, you create the next pair, you just can't encode it the way you want. And what will you find in the whole literature, they simply won't talk about the pair creation. The horizon, they'll keep repeating, this is what I want, this is what I want, but what they want is a piece of code.
I think in the interests of getting
Yes,
to the
sorry.
end of things, we should move on, because we've got the Hayden-Preskel thing to talk about and the small corrections theorem to talk about. We should try and wrap up in about 15 to 20 minutes. So I think it's over to you,
I think that those two I was supposed to talk about,
yes,
because they were not really problems to do. And I won't say much about them. We won't actually go through them in detail. We've already talked about small correction theorem. So let me just mention again the relevance of that. I won't go through the proof, because the proof, if you want a brief version with the second of these, note 1309, one, you can just see it's like a 5-line proof. But I do encourage everyone to actually work through that. But the importance of this theorem is that I think almost everybody in the string part of the community, not in the GR community, was somehow thinking secretly that small corrections to the Hawking process will actually remove the entanglement, because there's so many little corrections, there's so many terms, and each one can be entangled with each. And the GR people just couldn't follow like why that could happen. And so, when Hawking said, I give up my thing in 2004, and I think Preskel was right, and I gave up my bet and so on, he was having in mind just these kind of small corrections, because he was saying, some subleading saddle point will do something or something. But any subleading saddle point, the Euclidean analysis is basically going to give you some small corrections in the Lorentzian formulation. And so I've just modeled them here in our toy model, where at each stage of the pair creation, you can say, okay, I can add some new piece, psi1. And the piece psi1 could be anything. It could depend on, or the epsilon one could be anything, could depend on anything which happened in the past. Psi1 could involve all the different bits which are in the black hole. It could do anything. So you do that, but to leading order, you do want a 0, 0 plus 1, 1 to come out, because you want a semi-classical physics. If that doesn't happen, you don't have your semi-classical physics. Because semi-classical physics tells you, if you have the vacuum on modes of a meter, the moment you stretch it to 10 meters, you'll have one pair of particles, nothing you can do about it. So you allow yourself anything for the epsilons, and you still find that you actually can't do that. So the entanglement doesn't go down. In fact, the maximum amount that you can get the entanglement to go down is that it goes down by a fraction, which is bounded by 2 epsilon. So if epsilon is, let's say, 0.01, your corrections are 1%, you can at most get it down to go by 2%. You can't make it go down by whatever order unity that you wanted. So if the small corrections won't help you, you need large corrections. And then you have to see, okay, how do I violate semi-classical physics at the horizon completely? And that's what a fuzzball gives you. So this is important, because initially when fuzzballs came up, people were saying, I don't want such a big correction at the horizon. I'm looking for something small. And this tells you, you can't actually have something small. So that's actually all I was going to say about it, but people should ask me questions about the small correction theorem. But the other one, the Hayden-Preskel paper, this is just an example of how people are actually talking about black holes in the beginning. But then when they start actually doing something, people can look at this paper or any other papers that people write, you will find that the moment they start doing something, they say, okay, I have this bit inside, it'll come out. But from the time they model it with bits, they're not actually modeling it like equation 25. They're actually modeling it like a piece of code. So the same bits which are inside are the ones which are going to come out. So the pair production step, which is a 0, 0 plus 1, 1, which was in problem 8 and problem 9, is actually missing from all of these papers. And so the point is, the moment you are actually not seeing the 0, 0 plus 1, 1, or 0, 0 plus 1, 1 plus some epsilon times a psi 1, if you're not seeing that in the paper, they're not even talking about a black hole. So this is the big disconnect, that what is actually happening with the island papers is they never talk about this equation 25. They don't worry about the fact that small corrections can't solve the problem. People like Malthus do sort of realize that they can't solve it this way, and then they actually have generally non-local impact. So if you have a wormhole by which you take the bit C inside and non-locally transfer it through a wormhole and put it near infinity, then you're okay. That's like saying the piece of coal, the ash doesn't come out floating out, it goes through a wormhole and it comes out. It can't float out because Malthus wants a smooth horizon. The light cones point inwards, so he can't get out of coming out like a piece of ash, but you can transfer it through a wormhole and take it out to infinity. So that's what you would call the non-local wormhole solution. That is always allowed. I don't believe it is true. There's nothing in string theory to say that that's what has happened, but note that you can do that. You're simply not transporting it all over space, but transporting it by a different connection through space-time, which is this wormhole. But keeping the smooth horizon, the fact you can't do it is the essence of problem 9, problems 8 and 9. And then problem 10, if you go and look at the paper, I'm not going to open the paper here because if you're not familiar with it, it won't tell you anything. But we'll do this later on with lots of papers one by one. Once we are familiar with the entire puzzle, we'll open some random paper from the island people or from this kind of paper doing information theory things and go through it and see, aha, at which point did they stop talking about the black hole with which they started and they modeled it like a piece of code. So this was just to say people should enjoy this paper or any other paper they want. And the results are all beautiful, but they're all equally true for a piece of code. So if you take a piece of coal and you keep letting it emit bits, then after it emits more than half the bits, at what rate the information comes out, they did a beautiful analysis of that, but it's for a piece of code. It doesn't come out for a black hole. So that's all I was going to say. I don't want to belabor the point here because I'm actually going to solve the small correction theorem here. You can just see it solved there. And I don't want to go through the hidden Pascal paper unless somebody wants to actually open it, but that was the import of the problem.
I just opened it, but is there some point where you can point to say, okay, this is where the bait and switch happens?
Okay, so let me also open it. Can you put in the share so I can click in it in the chat? So I'll click on it and it'll open for me also.
Well, I'm going to put the archive address.
Okay, yeah.
Oops, sorry, I just sent it to my students, everyone. Oops, there we go. Yep, there's the archive link.
So let me open it also.
So you're saying that these people are basically doing bait and switch.
So all these papers are bait and switch. I mean, hidden.
There we go. There's something provocative to finish on. But seriously, I'd like to see where the bait and switch happens.
Okay. So you can start right from. Okay. So let's start looking at the whole thing. So equation 2 is a normal entangled state.
Did you want to share the document, Samir?
Yes. So let's do that. So let's stop share that. I'll do a new share. Okay, can people see it now?
Yep.
Okay, so I'll start in the beginning because you can see they're talking about black holes in the beginning. So, okay, so there's a black hole right there, you can see. So, okay, so there's all the stuff about black holes there. Then, okay, these are just classical random things. Classical randomizer, there's nothing to do with the black hole there actually. Then they're just talking about bits, like if you mix up some bits and then you take them out. At this stage, already they're talking of bits. And if you read anything here, you would just see it's classical bits. Okay, there's no black hole or pair creation or making new bits out of the vacuum. Then you come to the quantum state. This is already something made of a certain number of bits, equation 2. If you have two entangled systems, this is the kind of entangled system that you have just seen everybody writing. If M is the smaller one, if just your system M, then N is an identical copy. This is one way to write an entangled state. It will give a density matrix on the first system labeled M. This was like the thermophile double state that was wrote. It's just a maximally entangled state of two systems. Okay, so far you haven't done anything with it. The time to start doing something is all in this figure, figure 1. So you will start with some bits here, and you will take some bits here, you will mix them up, you will emit a bit, and so on. This is just telling you have some bits, and you're going to shuffle them, and how you're going to emit them. So what do these pictures mean? You start with some 2 bits, a red bit and a green bit, which are entangled with each other. Here you have a blue bit and a black bit, which are entangled with each other. Then you take these 2 bits, you make them interact with each other so they can exchange something, we call something. That's what these figures mean. You're just taking spins, and the spins are entangled, and then you take one member of an entangled pair and a member of an entangled pair. You make them act with some Hamiltonian, which flips the spins or exchanges them. That's all that these figures mean. Okay? But let's see what they do with it. So then you can see them, they're just computing various density matrices and so on. And in all this calculation that you see, you'll find that they're actually working with a system of a given size. And this is all that's being done in all these steps. It's just the answer for a piece of coal where you had some n bits and you're taking some m size subset out of it. So all these equations now just correspond to a piece of coal. You're nowhere seeing the 0, 0 plus 1, 1 kind of new bits, entangled bits that are coming out, because they will just keep coming out. So they're going to go past the halfway point, but after the halfway point, it's this fixed system from which they're taking more bits out of the fixed system of total size, some total size n, and that's where this answer comes from. So in all of this, you will see that if they had actually put in that the fact that the bits were coming out in the original picture, the new bits coming out of the black hole were new bits which were entangled as 0, 0 plus 1, 1, none of what follows will actually work. You cannot start getting information after that. So you simply have to go through what they're trying to do here. And so right away in the next one, you will see that there is absolutely no relevance. So then they can keep talking about, how, so they're talking about is certainly very interesting for a piece of coal. Like after the halfway point, you get information out, but at what rate do you get it out? So if the black hole is mixing everything very rapidly, then it's, at what rate you get out. You just assume that the coal is mixing, not black hole, but a coal. The coal is mixing everything very rapidly. At what rate does it come out? When can you actually decode a bit? It's all true for a piece of coal. It's not true for a black hole. So that's what I was calling the difficulty with all these papers. The results are very beautiful and they are very correct for the piece of coal. But all they have assumed is if you have a piece of coal, which once it emits a photon, the remaining pieces in there, they reshuffle so quickly that you come to a randomized state. Then it emits a bit, they reshuffle so quickly that you come to a randomized state. Just given that, at what rate after the halfway point is the information being emitted? That's the answer. That's what they are computing. So it's a bit like the page paper where you already know you have a piece of coal, but exactly how it's rounded at the top. But it's all for a piece of coal. So yeah, you just have to look through equation 3, 4, 5, and that's what you see.
I guess in terms of pieces of coal, they've made your naughty list rather than your nice list.
Well, the calculation is very nice. I mean,
no, I'm making a joke about Santa, remember?
Pardon?
I'm making a joke about Santa Claus. He has a naughty and a nice list, and the naughty people get pieces of coal. Okay, bad joke, but we're coming up on time. So, Samir, do you want to wrap anything up and so forth, or talk about what's happening next week? Or?
Yeah, okay. So let me just say about next week. So we have seen a bit of, I think they've gotten all the essence of the black hole puzzle. We know what a black hole is like, how it creates the entangled pairs, just by harmonic oscillators getting, excited. And we've seen how to compute their entanglement. So this is all there is to the puzzle. But now we want to go closer towards why the island people are, saying what they are saying. And what we really want to extract from learning about the island people is that what they're really saying is that you have non-local effects which secretly take the information out from the black hole all the way to the radiation, right? And what is confusing there is that people seem to be hinting or suggesting that somehow you can actually not have the non-local effects. And still somehow, because everything is made of everything, you can get a semi-classical physics at the horizon in which everything looks okay in some effective physics, but still you can actually get it out without the non-local effects. And that is simply not true. And so with the small correction theorem and all, like we talked about, you can show it's not true. But how do you find the mistake in what they're doing? And so to find the mistake in what they're doing, you have to go and ask them, okay, so you are making the entangled pair. Where is the pair going? So where's your outside member? Where's your inside member? Who's entangled with who? So they're never addressing that. And so to understand what they're actually doing instead, what are these indirect arguments they are using? We now want to understand what is all this Euclidean stuff. Because when they do Lorentzian stuff, they actually do exactly what we have. They get the entangled pairs and they say we cannot reduce the entanglement. So then the only thing they say is that after the bits have come out, after the halfway point, you should include the bits inside the black hole, make it one common system, and then it's not entangled with anything. But that is not a solution to the problem. That's just redefining the problem. If you actually take the bits outside and pass it through a Stern-Gerlach, you'll actually find they're not entangled. They're not pure. They're entangled with the black hole if the black hole horizon was smooth. So it's not like a piece of coal. So why should you include the bits inside? This is an experimental difference. So then if you want to see how they came to their conclusions, why are they arguing the way they are, we are actually going to the Euclidean calculation of black hole entropy. So we'll do the Gibbons-Hawking calculation of entropy and see that all this Ryu-Takanagi thing that they are very interested in is basically Gibbons-Hawking in a different language. So they are using actually Gibbons-Hawking in a case which is not even a black hole. That suggests to them that areas are very important. And even though there's no black hole there, they say area is basic. Gibbons-Hawking had like sort of area coming in. So we'll use Euclidean ideas and the area kind of ideas and say the entropy of everything is bounded by the area. So the entire island formula that is called simply says the entropy of anything is bounded by the area, which is equal to what Bekenstein said way back in 72. You cannot put entropy in some region more than the area of that region. So that is put in as an input. It's not actually the result of a calculation. It looks like the result of a calculation, but it's actually not. So that's what we want to understand. It's the calculation actually just the Gibbons-Hawking calculation, which actually says that the Gibbons-Hawking answer for the entropy is equal to the area upon 4G. So if that was taken as the answer that this is actually the entropy of the black hole, there was no paradox from that time onwards. So the whole paradox is that the Euclidean answer is not the Lorentzian answer. So the next assignment will do the Lorentzian calculation of entanglement and then the Euclidean calculation and contrast them. So then we can start to see where the Hawking people, what the Allen people are thinking, why are they thinking what they are thinking, and how they are going down the path they are going down. Okay, that's what I was going to say. So are there any questions or comments for me?
Okay. So I've been trying to get a pigeon for next week to guide the conversation. I don't have any volunteers yet, but anybody step forward? Otherwise, I'll try and corner somebody offline. But otherwise, Samir and I will talk about it and figure out what to do. Okay, well, once again, thanks. And thank you especially to Mathur and to Bin for doing the early part of the heavy lifting, and of course to Samir for his really excellent commentary on the subject, and for people jumping in and making questions, asking questions, and Emil particularly. So any other final questions? We're coming up on the 5 o'clock hour, which is, I think, all most of us can take. But,
yeah, can I ask a question? So, Samir, you mentioned that for the first ball picture, we don't have a horizon, right? And you also mentioned that you're not considering any small corrections to the system. So I don't think I understand how come we don't have a horizon?
So let me see if I understood the question. The first ball is actually a construction in string theory where you try to make a object with some amount of charges, and you find it doesn't actually have a horizon. It's more like a piece of coal with no horizon. So then, of course, the small correction theorem is not even relevant because the horizon is not close to the vacuum. It's far from the vacuum. You have large corrections, and there is no puzzle. It radiates from its surface like a normal body. So what was the question about that?
Yeah, but it doesn't. So I don't find it intuitive. Like we don't. So it doesn't look like a black hole, right? It should be having a singularity and a horizon.
So it doesn't. So it doesn't look like a black hole, and that's the whole point of the fuzzball paradigm. That when you actually try to make black holes in string theory, you don't actually get black holes. When you try to make something which has a horizon, all these new degrees of freedom like strings and brains come up, and they just make a big ball, which is the size of the whole horizon. So you never actually end up making a black hole in string theory. You end up making one of these complicated objects instead. So why that happens? Yeah. So, but that, since we haven't talked about fuzzballs here, that wouldn't be clear. I'm just giving the answer for what a fuzzball is, why it happens, how the semi-classical intuition gets violated. Those are different things, but we haven't talked about them. So let me not.
So out of these things, what do you think is true? Like, so do we think Hawking's calculation is right because we also get a non-uniform result, but still it's right? Or do we think the fuzzball picture is right, or the island?
So I think the fuzzball picture is right, and the Hawking calculation is right in any theory which doesn't have fuzzballs. So if you don't have string theory, which is 3+1 dimensional canonically quantized gravity, the calculation is correct, and you will get information loss. There's nothing you can do about it. You will get either remnants or information loss, and you cannot actually get the unitary radiation the way these people want. And that's the whole problem with the island people also. They're using 2D gravity. It doesn't have the power to make a fuzzball with those degrees of freedom, and so you will actually have a smooth horizon, and you cannot get the information out. With all of string theory, you're finding that you don't get a horizon, and that's a very complicated construction. I mean, it uses all the facets of string theory, and it's certainly not obvious.
maybe I could just make a quick remark. I mean, we know that there's no information problem with a white dwarf, and we know that there's no information problem with a neutron star, and it's simply because a state of matter emerges that can stabilize the system. But the reason to some extent why, in fact, Eddington eviscerated Chandrasekhar is he removed Chandrasekhar's calculation showed that there would be a collapse of a white dwarf, and therefore probably it would wind up in what Eddington called this ridiculous state called a black hole. So unless you can stop the formation of a horizon, you have this information problem. Hawking's calculation is correct, everything about it is correct, But in order to solve this problem, you have to stop the horizon, a smooth horizon, from forming. And the neat thing about string theory is that it looks like there are other states of matter that are going to emerge from string theory that can arrest the collapse before the horizon forms. So that's what a fuzzball is. It's a statement that within at least string theory, there are states of matter that can support the structure of something that looks just like a black hole in astrophysics up until close to the horizon scale, and it replaces that horizon region with a fuzzball.
Thank you.
Okay, any other questions or comments or concerns? Joseph? Yeah.
No, I just want to thank Samir a lot. I mean, I've been watching everything on YouTube and, via Zoom and so on and so forth. Thanks. It was very useful. So.
Okay, thanks to everyone for coming.
Well,
Bye-bye.
thank you.
I'll stop the YouTube.